There are places in the universe so distant that even light, traveling at the fastest speed reality allows, will never arrive there in time to matter. Not in a billion years, not in a trillion, not ever. We like to think of space as empty. Vast, yes, but connected. We imagine galaxies scattered like islands across a cosmic ocean, separated by distance but still part of the same story. We assume that, given enough time, everything could eventually influence everything else. But what if that assumption is wrong? What if the universe is not merely large, but fundamentally isolating? When we say something is far away, we usually mean it in human terms. A city across a country, a planet across a solar system. Even another galaxy feels reachable in imagination. After all, light from distant galaxies reaches us every night. Telescopes capture their glow. They feel present. Yet presence is deceptive. When you look at a galaxy a billion light years away, you are not seeing it as it is. You are seeing it as it was a billion years ago. That light began its journey long before complex life existed on Earth. By the time it arrives, the galaxy may have changed completely, merged, evolved, perhaps even vanished. Distance is not just space, it is time. And in an expanding universe, distance is something else entirely. Space itself stretches. Galaxies drift apart not because they are moving through space like ships across water, but because the water itself is expanding between them. The farther away a galaxy is, the faster it recedes. Beyond a certain point, recession becomes permanent. No signal sent today will ever reach those regions. They are not simply far. They are causally disconnected. This is the beginning of real isolation. Isolation in the universe is not measured only in kilometers or light years. It is measured in the ability to interact. If two objects can never exchange light, never share gravity, never influence each other even in principle, are they part of the same reality? We exist in a moment when the night sky is full. Thousands of galaxies are visible with the right instruments. The cosmic web, an immense structure of filaments and clusters, connects matter across billions of light years. Everything appears woven together, but that is temporary. As dark energy accelerates expansion, structures drift beyond each other's horizons. Over unimaginable timescales, galaxies will disappear from view. Observers in the distant future may see only their own local cluster, isolated in darkness, unaware that others ever existed. The universe is not static. It is dividing. And within that division lie regions already so empty, so sparsely populated, that a single galaxy can drift for hundreds of millions of light years without encountering another. There are voids, enormous cosmic cavities, where almost nothing resides, no clusters, no bright neighbors, just faint, scattered matter, suspended in expanding darkness. In those places, isolation is not metaphorical, it is structural. But perhaps the most unsettling possibility is this. The most isolated object in the universe may not be located in some distant void. It may be a future inevitability, a time when every galaxy becomes alone, a time when interaction becomes impossible, a time when the cosmos no longer feels like a connected whole, but like fragments drifting beyond one another's reach. So what is the most isolated object in the universe? Is it a galaxy stranded in a void, a black hole wandering through empty space, a lone star far from any cluster? Or is it something far smaller, a single particle, separated by unimaginable distances from everything else? To answer that question, we first have to understand just how empty the universe truly is, and how emptiness itself evolves. Part 2. The scale of nothing. To understand isolation, we have to confront something uncomfortable. The universe is not mostly filled with galaxies. It is mostly filled with nothing. When we look at deep field images from space telescopes, the sky appears crowded. Thousands of galaxies packed into a tiny patch of darkness. Spirals, ellipticals, irregular clusters, glowing structures layered across cosmic depth. It gives the illusion of density, as if the universe is saturated with matter. But that image is deceptive. Those galaxies are separated by immense distances. The space between them is not gently spaced. It is overwhelming. If the Milky Way were reduced to the size of a coin, the nearest large galaxy would be another coin several meters away. And that is within our local group, which is considered gravitationally bound and relatively dense. On larger scales, the separation grows extreme. The average distance between major galaxies can be millions of light years. Between clusters of galaxies, tens or even hundreds of millions. And between the largest structures, the cosmic voids, the emptiness becomes almost incomprehensible. Even within galaxies, most of the volume is empty. The distance between stars and the Milky Way is vast compared to their size. If our sun were the size of a marble, the nearest star would be thousands of kilometers away. Planets are even smaller by comparison. Atoms themselves are mostly empty space, nuclei surrounded by vast probability clouds. Emptiness is not an exception. It is the rule. The universe is not a solid tapestry of matter. It is a sparse framework of luminous islands suspended in a nearly infinite vacuum. And that vacuum is colder and thinner than any environment we can truly imagine. The density of intergalactic space is roughly 1 atom per cubic meter. Not 1 molecule, 1 atom. In some regions, even less. Compared to the air you breathe, which contains trillions upon trillions of particles in a similar volume, intergalactic space is almost perfectly empty. Yet even that is not the most extreme case. There exist regions called cosmic voids, volumes spanning hundreds of millions of light years where galaxy density drops dramatically. These are not small pockets. Some voids are larger than entire galaxy clusters. They are enormous cavities in the cosmic web where matter failed to accumulate during structure formation. Inside a void, a galaxy might drift for millions of light years without encountering another. Light from neighboring structures may be so faint and distant that the sky appears almost black. Isolation is not rare. It is built into the architecture of the cosmos. The cosmic web itself, the grand structure of matter, resembles a network of filaments and nodes with vast empty spaces between them. Galaxies cluster along the filaments. Clusters form at the nodes. But the majority of the universe's volume lies in the gaps. In other words, most of reality is absence. When we speak of the most isolated object, we are not searching in a dense landscape. We are searching in an environment where separation is the default condition. Distance on Earth is intuitive. You can measure it, cross it, reduce it. But in the universe, distance is not merely a matter of travel time. It is compounded by expansion. The space between objects grows over time. 2 galaxies separated by millions of light years today may be separated by tens of millions in the future. Isolation increases. The universe does not merely contain emptiness, it produces more of it. And within that growing emptiness, certain objects become increasingly cut off, not because they move faster, but because the fabric between them stretches beyond recovery. To grasp the scale of nothing is to realize that connection in the universe is fragile. Structures form locally, bound by gravity. But beyond those boundaries, expansion dominates. Matter thins, interaction fades. If isolation is defined by the inability to interact, then the scale of nothingness is the foundation of the problem, because the universe is not a crowded city. It is an archipelago drifting in an ocean that grows wider every second. And somewhere within that ocean, an object may already exist that is more alone than anything we have ever imagined. Part 3. The Cosmic Web. If the universe were perfectly random, matter would be spread evenly in all directions, a smooth fog of particles expanding forever. But it is not smooth, it is structured, and that structure determines where isolation becomes extreme. On the largest observable scales, the universe resembles a vast network known as the cosmic web. Galaxies are not distributed uniformly. They gather along enormous filaments, thin, thread-like structures of dark matter, and gas stretching across hundreds of millions of light-years. These filaments intersect at dense nodes where galaxy clusters form. Between the filaments lie enormous voids, vast regions where matter is scarce. This structure did not appear by accident. In the earliest moments after the Big Bang, tiny quantum fluctuations were stretched across cosmic scales during inflation. These fluctuations created slight differences in density, variations so small they were nearly uniform. But gravity amplifies differences. Regions slightly denser than average pulled in more matter. Regions slightly less dense lost it. Over billions of years, these imbalances grew into the web-like architecture we observe today. Dark matter played the dominant role. It does not emit light, but it provides the gravitational scaffolding upon which ordinary matter accumulates. Galaxies formed where dark matter halos became dense enough to trap gas. Filaments formed where matter flowed along gravitational gradients toward the densest nodes. The result is a universe shaped like a sponge or neural network, luminous strands surrounded by immense cavities. If you could zoom out far enough, galaxies would not look like scattered points. They would resemble beads strung along invisible threads, with yawning expanses between them. These expanses are not small. Some voids span over 100 million light-years. Others are even larger. Compared to the size of a galaxy, which might be 100,000 light-years across, these empty regions are colossal. Isolation is built into this design. Within filaments, galaxies are relatively close. They interact gravitationally, they merge, they exchange gas, they influence one another's evolution. But inside voids, interactions become rare. A galaxy located deep within a void may have no significant neighbors for tens of millions of light-years. From its perspective, the sky would look different. The density of visible galaxies would be lower. The gravitational pull from surrounding structures would be weaker. The local environment would evolve more slowly, more quietly. The cosmic web is not static. Matter continues flowing along filaments toward clusters. Voids expand as matter drains from them. Over time, the contrast sharpens. Dense regions become denser. Empty regions become emptier. Isolation intensifies. And because the universe is expanding, accelerating, in fact, The separation between these structures increases not just due to gravitational redistribution, but due to the stretching of space itself. Imagine a network drawn on rubber. As the rubber stretches, the filaments lengthen, nodes drift farther apart, the gaps widen, the pattern remains, but its scale increases. That is what is happening to the cosmic web. The largest structures remain gravitationally bound locally. Galaxy clusters will not simply drift apart internally, but clusters separated by vast voids will eventually recede beyond each other's observable horizons. In that sense, the cosmic web contains the seeds of future solitude. Right now, we observe a connected universe. Even distant galaxies are linked through shared history and gravitational influence. But in deep time, those links will weaken. If you lived in a galaxy located on the outer edge of a filament near the center of a massive void, your cosmic neighborhood would already be sparse. Over billions of years, that sparsity would increase. Neighboring filaments would drift farther away. Distant clusters would fade from view. Your galaxy would remain bound internally, stars orbiting its center, planets circling stars. But the larger network would dissolve from your observable reality. The cosmic web gives the illusion of connection, but its geometry also creates isolation by default. The most isolated object in the universe is not simply located far from others. It is located where the web thins to almost nothing, where gravity failed to gather matter into dense clusters, where voids dominate volume, and where expansion steadily erases the visibility of distant structures. The web connects, but it also separates, and in its vast cavities, we begin to approach the true scale of cosmic loneliness. Part 4. Cosmic Voids, the True Emptiness. If the cosmic web is the skeleton of the universe, then cosmic voids are its vast, hollow lungs, regions where almost nothing resides. Not absolutely nothing, but close enough that the difference becomes philosophical. A cosmic void is not an empty bubble carved out deliberately. It is the natural consequence of gravity working unevenly. In regions where matter density was slightly lower in the early universe, less material accumulated over time. As surrounding filaments grew denser, they pulled matter away from these underdense zones. The imbalance amplified. Voids did not explode into existence. They were drained. Imagine matter flowing downhill across cosmic terrain. Dense regions act like valleys, pulling material inward. Less dense regions lose that material and become increasingly hollow. Over billions of years, the contrast becomes dramatic. Some voids span tens of millions of light years. Others exceed 100 million. The Botas void, one of the most famous examples, stretches across roughly 330 million light years. Within it, the number of galaxies is drastically lower than average. Not zero, but shockingly close. If you could stand inside such a void, ignoring for a moment that standing in intergalactic space is not physically meaningful, the sky would look unnervingly sparse. Instead of countless galaxies in every direction, you might see only faint, distant structures near the void's boundary. The center would feel cosmically abandoned. Voids are not completely devoid of matter. There are still stray galaxies, dark matter, and thin intergalactic gas. But density is so low that gravitational interactions are weak. Galaxy mergers are rare. Large-scale structure growth is minimal. Evolution inside a void proceeds differently. Galaxies within voids tend to be smaller, less disturbed, and often more isolated. They do not experience frequent gravitational harassment from neighbors. They drift quietly, forming stars at their own pace, largely unaffected by external collisions. In a way, void galaxies live in cosmic solitude, but even this solitude is relative, because voids themselves are not fixed. As the universe expands and as dark energy accelerates that expansion, voids grow larger. Matter continues flowing outward from them toward filaments. The emptiness deepens. Regions that were once marginally connected become increasingly detached. Over extremely long timescales, voids may dominate the observable universe. From the perspective of an observer in the far future, their galaxy may sit within a region that resembles today's voids, surrounded by expanding darkness with no visible clusters beyond the local group. The most isolated object in the universe might not be isolated today. It may be isolated tomorrow. Voids represent more than emptiness. They represent the trajectory of cosmic separation. They show us how structure drains away, leaving behind expanding regions of near nothingness. But here is the unsettling part. Even voids are not perfectly empty. Quantum fields permeate space. Dark energy fills every region uniformly. Even in the deepest void, space-time itself is active at the smallest scales. True emptiness may not exist at all. Yet on macroscopic scales, voids come closest. If you wanted to search for the loneliest galaxy in existence, you would not begin in a dense cluster glowing with thousands of stars. You would search the heart of a void, where interactions are rare and neighbors are unimaginably distant. Some galaxies exist on the edges of these regions, some drift near the center, and among them, there may be one whose nearest significant companion lies so far away that, for all practical purposes, it lives alone in the cosmic dark. Voids are not mistakes. They are structural inevitabilities, and within them, isolation stops being poetic. It becomes measurable. Part 5. The Boötes Void. There is a region in the sky, in the direction of the constellation Boötes, that once unsettled astronomers for a simple reason. It seemed too empty to exist. When large-scale galaxy surveys began mapping the distribution of matter across the universe in the late 20th century, researchers expected variation. They expected clusters and filaments. What they did not expect was a cavity so large that it appeared almost unnatural. The Boötes void spans roughly 300 million light-years across. To grasp that scale, remember that the Milky Way is about 100,000 light-years in diameter. The Boötes void could swallow thousands of galaxies the size of ours and still have room to spare. And yet, it contains astonishingly few. It is not completely empty. There are galaxies within it, but their number density is dramatically lower than average. If you were located near its center, the nearest large galaxy might lie tens of millions of light-years away. That distance changes everything. Galaxies interact gravitationally over long timescales. Even distant neighbors exert tidal forces. They influence gas inflows, mergers, star formation rates. But in the deep interior of a massive void, these influences weaken to near insignificance. A galaxy there evolves almost undisturbed. Astronomers initially questioned whether the Boötes void was a data artifact. A region that large and that empty felt statistically unlikely. but further surveys confirmed it. The cosmic web truly contains enormous cavities where structure formation was suppressed from the beginning. The existence of such a void reveals something fundamental about the universe. Matter does not distribute evenly, and the absence of matter can be just as important as its presence. Inside the Bode's void, galaxies are sparse, widely separated, and often smaller. Many are blue and actively forming stars, suggesting they have experienced fewer disruptive mergers. In dense clusters, galaxies collide and merge frequently. In voids, collisions are rare. Isolation shapes identity. Imagine a civilization living on a planet inside a galaxy near the center of such a void. Their night sky would look different from ours. Instead of a faint band of distant galaxies visible through powerful telescopes, there might be almost nothing beyond their local stars. Over billions of years, as expansion accelerates, even those distant edge galaxies would drift farther away. The observable universe from that vantage point would shrink in terms of visible structure. The Buddha's void is not the only void. It is simply one of the most famous and dramatic examples. Surveys reveal many such regions, each representing zones where initial density fluctuations were low enough that matter drained outward rather than accumulated. Voids grow over time. As matter flows into filaments, the cavities expand. The contrast sharpens. Dense regions become denser. Empty regions become emptier. If isolation is defined by minimal interaction, then galaxies inside deep voids are already candidates for the most isolated objects in the present universe. But the Bode's void also teaches a humbling lesson. Even a structure that feels unimaginably empty on human scales is still part of a larger network. It is bounded by filaments. It interacts gravitationally at the largest scales. It is not absolutely disconnected. The most isolated object in the universe may not exist today in its final form, because expansion continues, because horizons shift, because regions that are merely distant now may become permanently unreachable later. The Buddha's void shows us how emptiness forms, but it may only be a preview of something far more extreme, a future in which entire galaxies become stranded not within a cavity of the web, but beyond the web itself. Part 6. A galaxy. Alone. Inside a massive cosmic void, there are galaxies that exist in conditions so quiet they almost seem unreal. No constant gravitational harassment from nearby clusters. No tidal distortions from frequent mergers. No bright neighboring spirals dominating the sky. Just a slow rotation of stars around a dark matter halo, unfolding in near isolation. These are known as void galaxies. They are not fundamentally different in composition from galaxies elsewhere. They contain stars, gas, dust, dark matter. Some form new stars actively, others evolve more gradually, but their environment shapes their destiny in subtle ways. In dense regions of the universe, galaxies rarely live peacefully. They collide, merge, strip gas from one another, trigger bursts of star formation, distort shapes, and feed central black holes. Clusters are violent ecosystems. Motion is constant. Influence is unavoidable. Void galaxies experience something else: silence. Their nearest significant neighbors may lie tens of millions of light years away. On cosmological scales, that is a gulf. Gravitational interactions drop sharply with distance. The tidal forces that reshape galaxies in crowded clusters become negligible. A void galaxy can rotate for billions of years without major disturbance. This changes everything about how it grows. Without frequent mergers, its structure may remain relatively undisturbed. Spiral arms can persist longer. Gas can settle calmly into disks. Star formation proceeds in a more measured rhythm. The galaxy becomes, in a sense, internally focused, evolving based on its own mass and internal dynamics rather than external pressure. But isolation has limits. Even in a void, a galaxy is still part of the cosmic web. Dark matter filaments extend faintly through these regions. Intergalactic gas drifts across vast scales. Light from distant structures still travels through space. Isolation is never absolute, yet it can become profound. Imagine standing on a planet orbiting a star in such a galaxy. With advanced telescopes, you scan the sky beyond your local spiral structure. You expect to see distant galaxies scattered across the darkness. But instead, you find very few. The sky appears sparse. The large-scale structure is faint and distant. Your cosmic neighborhood feels small, and over time, it becomes smaller still. As dark energy drives accelerated expansion, distant galaxies recede faster and faster. The ones near the edge of the void drift outward. Eventually, their light redshifts beyond detectability. Even if they still exist, they fade from view. A void galaxy today may become a completely isolated island in the future. And this is where the concept of isolation deepens. Because isolation is not just about present separation, it is about future impossibility. A galaxy might currently have distant neighbors, but if expansion ensures that no signal can ever reach them again, then in practical terms, it becomes alone. There are galaxies already near this threshold. They sit in underdense regions where large-scale gravitational influence is weak. Their connection to the broader cosmic network is tenuous. As billions of years pass, that connection will stretch and thin until it effectively disappears. The most isolated galaxy might not be one sitting in the deepest void today. It might be one positioned such that in the long future, every external structure drifts beyond its cosmological horizon. Inside that galaxy, stars will continue burning. Planets will orbit. Black holes will consume matter. Internally, life could persist for unimaginable spans of time, but externally, the universe will fade. From that vantage point, isolation becomes existential. Not just physical distance, but informational separation. No new light, no incoming radiation from distant galaxies, no evidence that anything beyond the local structure ever existed. A galaxy alone is not a fantasy. It is a forecast. Part 7. The loneliest galaxy ever found. Astronomers have spent decades mapping the large-scale structure of the universe, cataloging galaxies and measuring their environments. Some are found in crowded clusters containing thousands of neighbors. Others lie in loose groups. But a rare few exist in environments so sparse that they approach the limits of cosmic solitude. One such example is a galaxy known as MCG plus 01-02-015. It does not have a dramatic name. It does not sit in a famous constellation glowing brightly for amateur observers. But its location makes it extraordinary. It resides deep within a cosmic void, with its nearest significant galactic neighbor roughly 100 million light-years away. 100 million light-years. For comparison, the Andromeda Galaxy, our closest large neighbor, is only about 2.5 million light-years away. That is considered nearby on cosmic scales. A galaxy isolated by 100 million light-years is not simply distant, it is marooned. If you lived inside MCG plus 01-02-015, your telescopes would reveal a profoundly empty sky beyond your own galaxy's stars. The faint smudges of distant galaxies would be sparse and widely scattered. Large clusters would appear as distant ghosts, barely detectable against cosmic darkness. From within such a galaxy, the universe would look smaller. This galaxy is not unique in being located inside a void, but it is one of the clearest examples of extreme isolation in the present epoch. Its environment is so underdense that interactions are practically non-existent. No nearby galaxies distort its shape, no tidal streams connect it to companions. It evolves almost entirely on its own terms. And yet, even this is not the final form of isolation, because today, however distant its neighbors may be, light from them can still reach it. Signals could, in principle, be exchanged. Gravitational influence, however faint, still propagates. The deeper question is not which galaxy is currently the most isolated. It is which galaxy will become permanently cut off. As cosmic expansion accelerates, driven by dark energy, distant galaxies recede faster and faster. Beyond a certain distance, recession speed exceeds the speed of light due to the expansion of space itself. This does not violate relativity. Nothing moves through space faster than light, but space between objects expands so rapidly that signals can never bridge the gap. When that threshold is crossed, isolation becomes absolute. A galaxy like MCG plus 01-02-015 may one day reach a point where every other major structure lies beyond its cosmological horizon. No new light will ever arrive from beyond its local region. Observers there, billions or trillions of years at the future, might detect only their own galaxy and perhaps a few gravitationally bound companions. They would have no evidence of the cosmic web, no knowledge of galaxy clusters, no observable proof of a once-connected universe. The loneliest galaxy ever found today is lonely by density, but the loneliest galaxy of the future will be lonely by physics. Its isolation will not be temporary or relative. It will be enforced by the expansion of space-time itself. And from inside that galaxy, the universe would appear static and small, a single island of stars surrounded by eternal darkness. The irony is unsettling. We live in a time when the universe appears richly connected. Telescopes reveal billions of galaxies. The cosmic microwave background tells us of a shared origin. Large-scale maps show filaments stretching across unimaginable distances. But this view is temporary. There may come a time when an observer in the most isolated galaxy looks outward and sees nothing beyond their own structure. No evidence of the greater cosmos, no trace of the web, only their own stars. If isolation is measured by the inability to know that anything else exists, then the loneliest galaxy is not merely the one farthest from its neighbors, it is the one destined to forget them. Part 8. When light takes billions of years. Isolation in the universe is not only about space, it is about time, and time in cosmology behaves differently from anything we experience on Earth. When we speak of billions of light years, we are not describing a simple distance. We are describing a delay so immense that interaction becomes distorted beyond intuition. Light is the fastest signal possible. Nothing travels faster. No information can outrun it. When a photon leaves a galaxy 1 billion light-years away, it carries a snapshot of that galaxy's past. It does not show us the present, it shows us history. By the time the light arrives, the emitting galaxy may have changed entirely, merged with another, altered its structure, exhausted its star formation, or even ceased to resemble what we observe. In that sense, even connected objects are disconnected. We never see them as they are. We see them as they were. And in an expanding universe, the situation grows more severe. Space itself stretches as light travels. Wavelengths lengthen, energy decreases, signals weaken. A photon that began its journey in ultraviolet light may arrive stretched into infrared or even radio frequencies. Its information is diluted by expansion. Its origin becomes harder to reconstruct. The farther away a galaxy lies, the more extreme this effect becomes. Now imagine a galaxy positioned deep within a void. Its nearest neighbor may already be tens of millions of light-years away. That means any exchange of light between them takes tens of millions of years one way. A two-way conversation would require twice that time. In human terms, that is meaningless. In cosmic terms, it is already near the edge of practicality. But the deeper problem emerges when expansion accelerates. As dark energy drives the universe to expand at an increasing rate, distant galaxies recede from one another faster and faster. Beyond a certain threshold, known as the cosmological event horizon, light emitted today will never reach certain regions. Not in 10 billion years, not in a trillion, not ever. This creates a boundary not of visibility alone, but of causality. If a galaxy crosses beyond your cosmological horizon, no signal you send will ever reach it. No signal it sends now will ever reach you in the future. It is not merely distant, it is causally severed. From that moment onward, its existence becomes observationally irrelevant. Now consider a galaxy already positioned in a low-density region of the cosmic web. It has fewer neighbors to begin with. As expansion continues, those few neighbors drift away. One by one, they pass beyond the horizon. Their light redshifts, fades, and disappears. Eventually, the sky empties. This process is gradual, but relentless. Observers within such a galaxy would notice distant galaxies becoming dimmer over billions of years. Redshift would increase, structures would thin. And then, beyond some epoch, only gravitationally bound companions, perhaps a few satellite galaxies, would remain visible. Everything else would vanish from view. The universe would shrink, not physically, but observationally. This is not speculation detached from physics. It is the direct consequence of accelerated expansion confirmed by measurements of distant supernova and the cosmic microwave background. Dark energy ensures that large-scale isolation increases with time. The most isolated object in the universe may not be defined solely by its present coordinates. It may be defined by its future horizon. A galaxy could currently be moderately connected, but if its surroundings are positioned such that expansion will carry them permanently beyond its reach, then in deep time it will become alone in a way no present void galaxy fully is. Light is the final thread of connection. When even light cannot bridge the gap, isolation becomes absolute, and the universe, once woven together by filaments and clusters, transforms into a collection of separated islands, each bounded by its own horizon. Within those islands, life could continue. Stars could burn, planets could orbit, black holes could grow. Internally, everything functions, but externally, the greater cosmos ceases to exist. not because it is destroyed, but because it can no longer be seen. Isolation is not a dramatic explosion, it is a fading of signals. And in an expanding universe, fading is inevitable. Part 9. Isolation in an expanding universe. If the universe were static, isolation would be a matter of geometry. Measure the distance between objects, calculate gravitational influence, determine whether signals could eventually cross that space. The question would be finite and predictable, but the universe is not static. It expands, and not only expands, it accelerates. This changes everything about isolation. In a static cosmos, two galaxies separated by 100 million light-years would always remain separated by that distance unless gravity drew them together. Given enough time, light could cross that gap. Signals could, in principle, travel. Causality would remain intact. In our universe, distance is not fixed. Space itself stretches between galaxies. The farther apart they are, the faster that stretching occurs. This is not motion through space, it is motion of space. Two galaxies may remain stationary relative to their local environments, yet the metric between them increases. For nearby galaxies, gravity overcomes expansion. The Milky Way and Andromeda are moving toward one another. They are gravitationally bound. Expansion does not tear them apart. On local scales, gravity wins. But beyond certain scales, gravity loses. Clusters of galaxies remain bound internally, but clusters separated by vast voids drift apart. Superclusters, once thought to be permanent structures, are not gravitationally bound in their entirety. They too will disperse over time. There exists a critical scale in the universe, beyond which objects are no longer bound, and expansion dominates permanently. That scale defines future isolation. As dark energy drives acceleration, the rate at which distant galaxies recede increases. The Hubble radius, the scale at which recession velocity equals the speed of light, becomes more significant. Objects beyond that scale today are already receding faster than light due to the expansion of space. We can still see them because their light was emitted long ago when they were closer. But light emitted from them now will never reach us. This creates a moving boundary in space-time, the cosmological event horizon. Anything beyond that horizon is permanently inaccessible, no matter how long you wait, no matter how advanced your technology becomes, no matter how powerful your telescopes are. Signals cannot cross. In such a universe, isolation is not just about low density, it is about horizons. A galaxy situated near the edge of a large void today may already have distant neighbors whose current light is the last it will ever receive. Over billions of years, those neighbors will fade. Redshift will stretch their light into invisibility. Eventually, they will cross the horizon entirely. From the inside of that galaxy, the universe will appear to contract. Fewer galaxies will be visible. The cosmic microwave background will redshift further, cooling and dimming. The sky will become darker, not because stars vanish internally, but because distant structure leaves the observable domain. Isolation deepens with time. If you imagine the cosmic web as a vast interconnected network today, then in the far future it will resemble scattered islands, each surrounded by unbridgeable darkness. The most isolated object in the universe may not be isolated today in absolute terms. It may be one whose position ensures that, in the distant future, It retains no observable evidence of anything beyond its own gravitationally bound region. Expansion does not violently separate galaxies that are bound. It gently but relentlessly increases the gulf between those that are not. The key insight is this: isolation in the universe is not only spatial, it is temporal and causal. It depends on when you observe, not just where. Right now, the universe feels large but connected. We detect light from billions of galaxies. We map structure across vast distances. But this connectivity is time-sensitive. It exists because we live during an epoch when light from distant regions still reaches us. Future observers may not have that privilege. To them, the universe could appear as a single galaxy floating in darkness, with no trace of the cosmic web that once spanned billions of light years. Isolation is not a rare anomaly. It is the ultimate direction of cosmic evolution. Part 10. The Point of No Return. There is a boundary in the universe that no spacecraft can cross, no signal can penetrate, and no amount of patience can overcome. It is not marked by a wall or a flash of light. It does not announce itself. It is woven into the expansion of space itself. This boundary is the cosmological event horizon. It is easy to misunderstand what that means. We are familiar with the event horizon of a black hole, the point beyond which nothing, not even light, can escape. The cosmological event horizon is different in mechanism, but similar in consequence. It is the distance beyond which events occurring now will never influence us, because space expands too quickly between us and them. Imagine standing in a galaxy in a universe dominated by dark energy. You look outward at distant galaxies. Some are relatively close. Their light reaches you easily. Others are so distant that their recession velocity, due to expansion, exceeds the speed of light. You can still see them because their light began its journey long ago when they were closer. But light they emit today will never reach you. That is the point of no return. As time passes, more and more galaxies cross this threshold, not because they suddenly accelerate through space like rockets, but because the metric of space between you stretches faster than light can compensate for. There is no dramatic crossing moment visible in the sky. There is only gradual disappearance. Galaxies grow dimmer as redshift increases. Their light stretches into longer wavelengths. Eventually, it shifts beyond detection. Then, one day in the far future, their signals emitted from that point onward are simply gone, forever unreachable. For an observer inside a galaxy located in a sparse region of the cosmic web, this process becomes even more severe. With fewer nearby structures to begin with, each one that crosses the horizon represents a significant fraction of the observable universe. At some epoch, only gravitationally bound companions remain visible, perhaps a small group of galaxies orbiting a shared dark matter halo. Beyond that, nothing. The event horizon does not destroy other galaxies. It erases them from your causal reality. This is the deepest form of isolation physics allows. Inside that horizon, interaction is possible. Outside it, interaction is permanently impossible. The concept is unsettling because it reframes distance. It is not about how far something is in light years. It is about whether its future can ever intersect with yours. Two galaxies might exist simultaneously in the same universe, but if they are separated by an expanding metric that prevents all future signal exchange, They might as well be in separate universes from each other's perspective. Isolation, then, is not merely about emptiness or low density. It is about horizons. Consider again the galaxy MCG plus 01-02-015 deep within a void. Today, it still shares the universe with distant structures. It can, in principle, receive light from them. But in the far future, many of those structures will pass beyond its event horizon. The most isolated object in the universe may be defined not by how empty its surroundings are today, but by how many structures remain within its future light cone. Eventually, only its own gravitationally bound region will remain causally connected. Inside that region, stars will age and die. Black holes will form. Stellar remnants will drift. Internally, physics continues. But externally, the universe shrinks to a single island. There is no drama when a galaxy crosses the cosmological event horizon. No flare, no shockwave. Just a subtle shift in the geometry of space-time that ensures future light will never bridge the gap. That quiet boundary is the true point of no return. And beyond it lies the ultimate version of cosmic loneliness, not because others cease to exist, but because they cease to matter. Part 11. Future Isolation. Right now, the universe still feels crowded. We detect galaxies in every direction. Deep field images show thousands packed into tiny patches of sky. The cosmic microwave background tells us we share a common origin with regions billions of light years away. It gives the impression of a vast but unified structure. But this unity is temporary. As the universe continues to expand under the influence of dark energy, large-scale isolation intensifies. Galaxies that are not gravitationally bound drift farther apart. Clusters separate, superclusters fragment. Over time, the web-like structure that currently defines cosmic architecture thins. In the distant future, tens of billions of years from now, observers within our own galaxy will notice something strange. Distant galaxies will no longer be visible. Their light will have redshifted beyond detectability, or will no longer arrive at all. The sky will look emptier than it does today. The Milky Way and Andromeda will have merged into a single elliptical galaxy, often called Milkomeda in simulations. That merged structure will remain gravitationally bound internally. Stars will orbit its center. Stellar evolution will continue. But beyond that local system, nothing will be visible. From within that future galaxy, it may appear that the universe consists only of a single massive structure surrounded by darkness. The cosmic microwave background, the faint relic radiation from the Big Bang, will also fade. Its wavelength will stretch further due to expansion. Its temperature will drop below detection thresholds for any conceivable instrumentation operating within that galaxy. The evidence of the early universe will effectively vanish. Future astronomers, living trillions of years from now, might conclude that the universe is static and small. They would see only their own galaxy. No expansion would be measurable. No distant supernovae would reveal cosmic acceleration. The broader structure of the cosmos would be inaccessible. Isolation would not only be physical, it would be epistemological. Knowledge of the larger universe would disappear because observational evidence would be gone. This is the direction in which cosmic evolution moves. The most isolated object in the universe might not be an anomaly today. It might be every galaxy in the future. As horizons shrink relative to observable structures, each gravitationally bound island becomes its own closed system. Signals cannot escape beyond certain scales. No new information enters from the outside. Even now, there are galaxies so distant that their future light will never reach us. We are already partially isolated from parts of the universe. We simply cannot perceive it yet, because we are still receiving ancient photons emitted when those galaxies were closer. Future isolation is gradual but inevitable under current cosmological models. Dark energy does not tear apart galaxies or solar systems. It does not rip atoms apart. It acts subtly on the largest scales. It stretches space between unbound structures until they become permanently separated. Over immense timescales, the universe transitions from a connected network to a collection of isolated pockets. Each pocket contains its own stars, planets, black holes, and remnants, internally active, externally silent. The most isolated object in the universe then may not be found by searching the deepest void today. It may be any galaxy living far enough into the future that the rest of the cosmos has slipped beyond its horizon. Isolation is not a rare state. It is the long-term destiny of structure in an accelerating universe. Part 12. The Last Galaxy in the Sky. Imagine looking up at the night sky and seeing only your own galaxy. No distant spirals, no faint smudges of remote clusters, no background glow of the cosmic microwave radiation, just a single, vast system of stars, and beyond it, total darkness. This is not science fiction, it is a prediction. Billions upon billions of years from now, the accelerating expansion of the universe will carry distant galaxies beyond the cosmological horizon. Light emitted from them will no longer reach observers inside gravitationally bound systems like ours. The cosmic web, once visible in grand scale, will fade from view. From inside that future galaxy, the universe will appear radically different from what we see today. Right now, even with modest telescopes, we detect galaxies millions and billions of light years away. The sky is layered with history. Every direction contains structure. There is depth. There is context. In the far future, there will be none. Only the merged remnant of the Milky Way and Andromeda, a single massive elliptical galaxy containing trillions of stars, will remain visible. Satellite dwarf galaxies, if still bound, may orbit quietly. But beyond that, the universe will appear empty. To these future observers, it may seem as though their galaxy is the entire universe. Without evidence of expansion, without detectable background radiation, without distant galaxies to measure redshift, cosmology itself would become impossible. The data required to reconstruct the Big Bang would be gone. The last galaxy in the sky would not merely be alone, it would be unaware. Isolation at that point becomes existential. It is not simply about distance, it is about the loss of observable truth. If intelligent life exists in that distant era, its astronomers might map the stars within their galaxy in exquisite detail. They might understand stellar evolution, black hole dynamics, planetary systems. But when they look outward, they will see nothing beyond their own gravitationally bound domain. They may conclude that the universe is static and eternal. They may never discover that billions of other galaxies once filled the sky. The loneliness would be structural, not emotional. There would still be immense complexity within that single galaxy. Stars would continue to shine for trillions of years, especially red dwarfs, which burn slowly and steadily. Planets could still orbit. Life could persist under the right conditions. But the larger cosmic context would be gone. Today, we live in a rare epoch. The universe is old enough for complex structures to exist, yet young enough that distant galaxies are still observable. We can measure expansion. We can detect the cosmic microwave background. We can map large-scale structure. Future observers will not have that privilege. For them, the last galaxy in the sky will define the universe. And in that sense, the most isolated object in the universe may not be a galaxy stranded in a void today. It may be any galaxy far enough into the future that it stands alone against the dark, with no evidence that anything else ever existed. Part 13. What if you lived there? It is one thing to describe isolation in terms of redshift, horizons, and large-scale structure. It is another to imagine living inside it. Consider a civilization evolving in a galaxy deep within a cosmic void, or trillions of years in the future when the rest of the universe has slipped beyond visibility. From their perspective, reality would feel contained. Their night sky would be rich, but only locally. Billions or trillions of stars would still populate their galaxy. Stellar clusters would glow. Nebulae would shimmer. Black holes would anchor the galactic core. Internally, there would be complexity, movement, and change. But beyond that system, nothing. No distant galaxies peppering the darkness. No evidence of filaments stretching across billions of light years. No cosmic microwave background whispering of a shared beginning. The sky would not hint at a grand web of structure. It would suggest confinement. Would they even suspect that anything lies beyond their galaxy? Without incoming photons from distant regions, without measurable expansion, there would be no direct data suggesting a larger cosmos. Their observable universe would effectively collapse to the scale of their own gravitationally bound structure. Their cosmology would begin and end with their galaxy. Perhaps they would theorize that other galaxies once existed. Perhaps faint relic signals could still be detected if their technology were unimaginably advanced. But as expansion continues, even those relics would fade below detectability. Isolation shapes knowledge. We often assume that the structure of the universe is an objective truth accessible to any sufficiently advanced observer. But access depends on epoch and location. We see the cosmic web because we live at a time when light from distant galaxies still reaches us. We detect the cosmic microwave background because it has not yet redshifted beyond our instruments. Future civilizations may not have that window. If you lived in the last galaxy in the sky, your understanding of reality would be narrower, not because you lack intelligence, but because evidence would be gone. This introduces a new layer of isolation, informational isolation. Even if other galaxies still exist beyond your horizon, they would be irrelevant to your physics. No experiment could reveal them. No signal could confirm their presence. They would be outside your causal domain. From your perspective, they would not exist. Now consider the psychological dimension. If intelligent beings evolved in such a galaxy, their sense of cosmic place would differ fundamentally from ours. We look up and see depth. They would look up and see boundary. Would they feel alone? Perhaps not emotionally. Life would still exist among stars, but cosmically, their universe would be singular. There is something humbling about the fact that we live in a rare era when the universe is still visible at scale. The cosmic web is not eternal in observable form. It is transient. The most isolated object in the universe may not experience loneliness as a feeling, but any civilization within it would experience a smaller cosmos. Isolation, then, is not only about matter distribution or expansion rates. It is about perspective, and perspective depends on when and where you are embedded in space-time. Right now, we are connected to the broader universe through light that has traveled billions of years. That connection will not last forever. One day, somewhere, observers may exist who cannot see beyond their own galactic horizon. To them, isolation will not be an anomaly. It will be the only reality they have ever known. Part 14. Black holes in isolation. If a galaxy can be isolated, and if a future universe can fragment into disconnected islands, then what happens at an even smaller scale, inside those islands, when structure itself begins to decay? Because isolation does not stop at the galactic boundary, it continues inward. Inside every large galaxy lies a supermassive black hole. In the Milky Way, it is Sagittarius A star. In future merged galaxies, that black hole will grow even larger as stellar remnants and smaller black holes fall inward. Over time, mergers will create a single dominant gravitational anchor at the center of each isolated galactic island. At first, that black hole is simply one object among trillions of stars. But as time stretches into trillions and quadrillions of years, stars begin to die. Star formation ceases as gas is exhausted. Massive stars burn out quickly. Smaller stars fade more slowly, but eventually even red dwarfs, the longest living stars, exhaust their fuel. Galaxies dim. White dwarfs cool, neutron stars lose heat, black holes remain. In a future where galaxies are already causally isolated from one another, internal structure also begins to simplify. Gravitational interactions slowly eject stars from galaxies. Close encounters between stellar remnants lead to slingshot effects, flinging objects into intergalactic space. Over incomprehensible timescales, galaxies gradually evaporate, not explosively, slowly. Stars are scattered outward. Some are captured by the central black hole. Others drift away into darkness. The once dense structure thins. Eventually, what remains inside that isolated galactic island may be dominated by black holes, the last gravitational strongholds of collapsed matter. Now, imagine a black hole existing in a universe where all other galaxies have crossed beyond the cosmological horizon. Its parent galaxy has long since dimmed. Most stars are gone. What remains is a sparse halo of cold remnants and a massive central singularity. That black hole becomes the most isolated object imaginable. No incoming light from distant galaxies, no external matter infalling from large-scale structure, no cosmic background radiation at detectable levels, only occasional encounters with drifting stellar corpses within its own shrinking domain. And even that will not last. Black holes are not eternal. According to quantum mechanics, they slowly evaporate via Hawking radiation. The process is unimaginably slow for supermassive black holes, far longer than the current age of the universe. But given enough time, even they fade. As the universe continues expanding, as galaxies internally decay, and as black holes evaporate, isolation deepens further. Consider the end state. a black hole alone in a dark, expanding universe, surrounded by no luminous matter, no incoming radiation, no gravitational neighbors within its horizon. Its only interaction is with the quantum vacuum itself. It radiates faintly, imperceptibly, losing mass over timescales so vast that human language struggles to express them. This is not dramatic cosmic violence, it is terminal quiet. Isolation, in its deepest form, is not a galaxy drifting in a void. It is a black hole in a universe that has forgotten everything else. And even that isolation is temporary, because once the black hole evaporates, what remains may be a diffuse bath of low-energy particles stretched thin by expansion. At that point, structure is gone. Interaction is nearly non-existent. The most isolated object may no longer be a massive structure at all. It may be a single particle drifting in an ocean of expanding space-time, with no neighbors within any meaningful distance. Isolation does not plateau, it compounds. From galaxies to voids, to horizons, to black holes, to particles. The hierarchy of separation grows more extreme with time. And in that deep future, isolation is no longer a property of location. It is the condition of existence itself. Part 15. The cold. Between structures. Before the universe becomes a graveyard of evaporating black holes, before galaxies dissolve completely into scattered remnants, there is another stage of isolation, one defined not by emptiness alone, but by temperature, because temperature is a measure of interaction. Where there is warmth, there are particles colliding, exchanging energy, radiating light. Where there is heat, there is activity. Where temperature drops toward absolute zero, motion slows, radiation thins, and interaction fades. The vast regions between cosmic structures are already unimaginably cold. Intergalactic space today is only a few degrees above absolute zero. The cosmic microwave background, the leftover radiation from the early universe, currently bathes everything in a faint glow of about 2.7 Kelvin. That glow is not permanent. As the universe expands, its wavelength stretches, its temperature drops. In trillions of years, the cosmic background will cool to temperatures so low that its photons will be nearly undetectable. The universe will not be filled with a faint glow anymore. It will be nearly perfectly dark. Inside voids, the situation is even more extreme. Voids are regions where matter density is already low. As expansion continues, they grow emptier. Gas becomes more diffuse. Radiation thins. Gravitational influence from distant structures weakens. Temperature falls further. Eventually, the space between galaxies becomes almost perfectly inert. No collisions, no heating, no external radiation. The cold between structures is not dramatic. It is quiet, passive, and relentless. If you imagine an object drifting through such a region, perhaps a rogue planet ejected from its galaxy during chaotic gravitational interactions, it would travel through darkness so complete that no external starlight illuminates it. No nearby stars warm it. No background radiation meaningfully interacts with it. It becomes thermally isolated, and thermal isolation deepens physical isolation. In the early universe, interactions were frequent. Density was high. Matter collided constantly. Radiation filled every region. The cosmos was hot, bright, and tightly coupled. Over time, structure formed. Density decreased globally. Voids expanded. Temperature dropped. Interactions became less common on large scales. The cold between structures is the intermediate step toward ultimate isolation. When temperature approaches absolute zero, motion becomes minimal. Quantum fluctuations remain, but classical interaction nearly vanishes. Particles can drift for immense times without encountering anything. The most isolated object in the universe might not be separated by distance alone. It might be separated by energy. Imagine a single proton drifting in a region where the average distance to the nearest other particle is measured in billions of kilometers, perhaps far more. No stars nearby, no galaxies visible, no measurable radiation, just a near-perfect vacuum. Its environment would not merely be empty, it would be thermodynamically silent. Temperature in such a region would approach the asymptotic limit of cosmic cooling. Interactions would be rare beyond comprehension. The proton's motion would be governed almost entirely by the expansion of space and quantum mechanics, not by collisions or radiation pressure. Isolation at that stage is no longer about being alone among galaxies. It is about being alone in terms of interaction probability. Cold is not just an absence of heat, it is an absence of engagement. The cold between structures tells us that the universe trends toward separation not only spatially and causally, but energetically. Stars once filled space with light. Galaxies once bathed their surroundings in radiation. But in the long arc of cosmic evolution, warmth recedes, darkness deepens, and the distance between meaningful interactions grows so vast that existence becomes nearly static. The universe does not end with fire, it cools into solitude. Part 16. Can isolation be absolute? We have followed isolation from galaxies drifting apart, to horizons sealing regions of space-time, to black holes evaporating in darkness, to single particles wandering through cold emptiness. But a deeper question remains. Can isolation ever be absolute? At first glance, it seems possible. Imagine a lone particle in a universe so expanded that no other matter exists within any meaningful distance. No stars, no galaxies, no radiation, no incoming signals. Nothing to collide with, nothing to exchange energy with. Is that not perfect isolation? Yet physics resists that conclusion. Even in the deepest void, even in the coldest epoch of the far future, space-time itself is not empty in the classical sense. Quantum field theory tells us that what we call vacuum is not nothing. It is a seething foundation of fluctuating fields. Virtual particles constantly appear and vanish. Energy density remains even in regions devoid of matter. The vacuum has structure. Dark energy permeates all of space. It does not cluster like matter. It does not thin inside voids. It remains constant per unit volume, driving expansion. Even if a particle drifts billions of light years from anything else, it is still embedded within this field. It cannot escape space-time itself. This means that no object can be isolated from the underlying fabric of reality. Isolation then becomes relative rather than absolute. A galaxy may be isolated from other galaxies, but not from dark energy. A black hole may sit alone in expanding darkness, but not from quantum fields. A proton may drift through near-perfect vacuum, but it remains subject to space-time curvature and vacuum fluctuations. Absolute separation would require an object existing outside the universe entirely, disconnected from space-time and its laws. That is not physically meaningful within our current understanding. Even at the ultimate end of cosmic evolution, in scenarios where matter decays, black holes evaporate, and expansion stretches everything beyond interaction, the vacuum persists. Quantum fluctuations remain unavoidable, and even more profoundly, Gravity never truly vanishes. If two particles exist anywhere within the same space-time, however far apart, they still influence each other gravitationally. The force becomes infinitesimally small at extreme distances, but it does not become zero. It falls off with the square of distance, approaching irrelevance, but never fully disappearing. Isolation, in the strictest mathematical sense, may therefore be impossible. There may always be some residual connection, however faint. But here is the unsettling twist. Physical connection does not guarantee meaningful interaction. A gravitational influence so weak that it cannot produce measurable effects is practically equivalent to isolation. A quantum fluctuation that cannot carry structured information is not communication. A dark energy field that expands space uniformly does not bridge objects together. The difference between non-zero and significant matters. The universe may never allow perfect mathematical isolation, but it trends toward practical isolation, a state where interaction probabilities become so low and signal exchange so impossible that objects effectively exist alone. This leads to a deeper realization. Isolation in the universe is not binary, it is asymptotic. It increases without bound, approaching a limit it may never quite reach. Galaxies drift beyond horizons. Black holes evaporate. Particles thin out. Temperature drops. Structure dissolves. Interaction becomes rarer and rarer. The most isolated object in the universe may not be completely cut off in absolute terms, but it may exist in a state where interaction is so unlikely, so negligible, that it might as well be alone forever. In that sense, isolation is not a final state. It is a direction, and the universe is moving steadily toward it. Part 17. Quantum fluctuations in emptiness. When we imagine isolation, we picture silence, stillness, a frozen scene where nothing moves and nothing changes. A particle suspended in perfect darkness, untouched by anything else. But the deeper we look into physics, the more that picture begins to crack. Because emptiness is not quiet. Even in the deepest cosmic void, even in a future where galaxies have slipped beyond horizons and stars have burned out, the vacuum is not a dead stage. It is an active field. Quantum mechanics refuses to allow perfect stillness. According to quantum field theory, every point in space is permeated by fields. The electromagnetic field, the electron field, the quark fields. These fields do not switch off in empty regions. They remain everywhere. And because of the uncertainty principle, those fields cannot be perfectly calm. There is always fluctuation. At the smallest scales, energy briefly appears and disappears. Virtual particles emerge for fractions of a second, then annihilate. The vacuum is not a static nothing. It is a restless baseline, a trembling floor of probability. Even if you isolate a single particle in an unimaginably vast, cold region of space, that particle is never fully alone. It interacts with the vacuum. Its properties are influenced by quantum fluctuations. Its mass and charge are affected by interactions with surrounding fields. Even in empty space, forces do not vanish. They merely become subtle. In fact, measurable effects emerge from vacuum fluctuations. The Casimir effect demonstrates that two metal plates placed very close together in vacuum experience a tiny force pushing them toward each other, not because of classical particles, but because of differences in vacuum energy between the plates and the surrounding space. Emptiness pushes back. This realization reframes isolation entirely. The most isolated object in the universe cannot escape quantum reality. It cannot detach from the underlying structure of space-time. It cannot become a self-contained entity floating in pure nothingness. Nothingness does not exist in the classical sense. Even if every galaxy drifts beyond the cosmological horizon, even if black holes evaporate, even if matter thins to single particles separated by unimaginable distances, the vacuum remains active. Energy density persists. Fluctuations continue. The universe, even at its coldest and most expanded, is not static. It vibrates at the smallest scales. This means that isolation is layered. On macroscopic scales, objects can become separated beyond interaction. On thermodynamic scales, temperature can approach near zero. On gravitational scales, influence can become negligible. But on quantum scales, the universe never truly stops interacting. The deepest void is still structured. The most isolated particle is still embedded. This does not erase isolation. It complicates it, because now the question becomes, what counts as meaningful interaction? If a lone proton drifts through space for trillions of years without encountering another particle, does it matter that quantum fluctuations still occur around it? Does it matter that dark energy continues to expand space? In one sense, yes. Physics continues. In another sense, no. No structured information is exchanged. No macroscopic event alters its path in a dramatic way. Isolation becomes scale-dependent. At large scales, separation dominates. At small scales, connection persists invisibly. The most isolated object in the universe may never achieve perfect detachment from reality, but it may approach a state where all significant interactions, collisions, radiation exchange, gravitational encounters become so rare that existence unfolds in near solitude. And yet, beneath that solitude, the quantum vacuum continues to shimmer. Even at the end of cosmic time, the universe refuses to become truly silent. Part 18. The ultimate lonely object. If galaxies can be isolated, if black holes can fade into thermal darkness, if even horizons can seal regions of space-time from one another, then what remains at the deepest layer of solitude? Not a structure, not a galaxy, not even a star. Perhaps the most isolated object in the universe is something far smaller. Imagine the universe trillions upon trillions of years from now. Galaxies have thinned, black holes have evaporated, stellar remnants have scattered. Expansion has stretched space so dramatically that the average distance between remaining particles is beyond any present comprehension. Now imagine a single proton, drifting, no nearby stars, no radiation bath, no gravitational structures within any meaningful distance, just an expanding metric and the faint tremor of quantum fields. It does not orbit anything, nothing orbits it. It does not collide, it does not emit, it simply exists. In that scenario, isolation is not about being in a void among galaxies. It is about being the only remaining structured object within a horizon of emptiness so vast that interaction probability approaches zero. But even this scenario demands scrutiny. Will protons even survive that long? Some theories suggest that protons may decay over extraordinarily long timescales, perhaps on the order of 10 to the power of 34 years or longer, if they decay at all. If proton decay is real, then even these last stable particles eventually dissolve into lighter components, positrons, photons, neutrinos. If proton decay does not occur, then protons may remain as some of the last stable building blocks of matter in a universe stripped of structure. In either case, what we are left with is not organized complexity, but sparse, drifting particles separated by distances that dwarf today's cosmic voids. Consider the scale. Today, the average separation between galaxies in voids might be tens of millions of light years. In the far future, separation between individual particles could exceed that scale. The universe continues expanding. Density drops further. Interaction cross-sections shrink relative to volume. The most isolated object in the universe may not be something massive. It may be something small, persistent, and alone. A single particle within a horizon so empty that the nearest other particle lies billions of light years away, perhaps more. In that state, interaction becomes statistically negligible. Gravitational attraction between such distant particles becomes meaningless over practical timescales. Collisions become virtually impossible. The particle drifts, influenced primarily by expansion and quantum fluctuations. There is something profoundly minimal about this image. No light, no structure, no complexity. Just a particle embedded in space-time. Yet even here, isolation is not absolute. The proton remains coupled to quantum fields. It interacts with the vacuum. Dark energy still drives expansion around it. Space-time curvature still defines its motion. It cannot detach from the fabric of the universe itself. But relative to every other particle, it may as well be alone. The ultimate lonely object may not be dramatic. It may not be visible. It may not even be large. It may be the final residue of matter in a universe that has expanded beyond structure, beyond warmth, beyond meaningful connection. A single quantum of existence in a sea of stretching space. And that raises a strange possibility. Perhaps isolation, taken to its limit, reduces everything to simplicity. From galaxies to black holes to particles, from structure to singularity, from complexity to drift. The most isolated object in the universe might not be grand. It might be small enough to fit within an atom, and far enough from everything else that for all practical purposes, it is alone, forever. Part 19. When interaction becomes impossible. There is a difference between being alone and being unable to interact. A galaxy in a void is alone in density. A future galaxy beyond a cosmological horizon is alone in causality. A drifting proton in deep time is alone in probability. But there exists a deeper threshold, a point where interaction does not merely become unlikely. It becomes effectively impossible. To understand this, we have to follow the universe into its most extreme, long-term projection. Heat death. Heat death is not an explosion. It is not a collapse. It is not a dramatic end. It is the gradual leveling of energy differences until no free energy remains to drive structure, motion, or information exchange. Every star burns because of imbalance. Every galaxy forms because of gravitational gradients. Every process in the universe depends on differences in temperature, density, pressure, curvature. When these differences vanish, interaction fades. In a universe expanding forever under dark energy, density approaches zero asymptotically. Matter thins. Radiation redshifts. Temperature drops closer and closer to absolute zero. At some stage, distances between remaining particles become so vast that even if they move randomly for trillions upon trillions of years, the chance of collision becomes negligible. Gravity still exists in principle. Quantum fields still fluctuate. But structured interaction, the kind that produces events, becomes vanishingly rare. Imagine two particles separated by billions of light years in a universe that continues expanding. Their gravitational attraction exists mathematically, but the expansion rate dominates. They will never meet. Not because a force forbids it, but because space-time stretches too quickly for attraction to overcome it. Now extend this to every remaining particle. Each one drifts inside its own expanding bubble of space-time with no realistic path toward meaningful encounter. Interaction does not drop to zero in a strict equation. It drops below relevance. There is no energy gradient to exploit, no star to warm a planet, no radiation to trigger chemistry, no collisions to create new structure. The universe does not become empty of existence. It becomes empty of events. The most isolated object in the universe may therefore be defined not by distance alone, but by its inability to participate in any future interaction. It cannot exchange energy. It cannot influence another object in any detectable way. It cannot receive new information. Its past connections are gone. Its future connections are impossible. It simply persists. This is a subtle but profound form of isolation. Earlier, isolation meant separation by space. Later, separation by horizons. Then separation by thermal silence. Now it becomes separation by entropy. When entropy reaches its maximum, nothing new can happen. No structure can form. No complexity can emerge. No meaningful interaction can occur. The universe does not shatter. It stalls. And within that stalled cosmos, any remaining particle exists in a kind of frozen autonomy. It is not imprisoned. It is not confined. It is simply surrounded by a reality so uniform, so diluted, so energetically flat, that interaction is mathematically irrelevant. The ultimate isolation may not be about being the only object. It may be about being unable to ever affect or be affected again. A universe where existence continues, but nothing ever happens. Part 20. The Last Observer. If isolation deepens with expansion, if galaxies drift beyond horizons, if black holes evaporate and particles thin into near impossible separation, then one question remains disturbingly human. What happens to the last observer? Imagine intelligence surviving deep into cosmic time. Not necessarily human, not biological in the way we understand it, but some form of structured awareness embedded within the final gravitationally bound island of matter. At first, this observer lives in a galaxy still populated by stars. They see structure, they map stellar orbits, they understand nuclear fusion, they measure black hole dynamics. Their universe appears rich, though finite. Then, gradually, the sky changes. Distant galaxies fade beyond detectability. The cosmic microwave background disappears into redshifted silence. Evidence of expansion vanishes from measurable scales. All external cosmology collapses inward. From their perspective, the universe contracts, not physically, but observationally. The last observer might spend millennia studying their galaxy, building theories about its origin. Without evidence of the Big Bang, without detectable background radiation, without observable expansion, they might conclude that the universe is static and eternal. They would be wrong, but their data would justify it. Isolation does not only remove interaction, it removes evidence. As stars die, the last observer watches their sky dim. Red dwarfs, the longest living stars, burn steadily for trillions of years. Eventually, even they exhaust their fuel. Stellar remnants cool. The galaxy becomes darker, colder, less dynamic. The observer may attempt to preserve energy, to harness black hole accretion, to slow entropy locally, to stretch their existence as long as physics allows. But no matter how advanced their technology, they cannot reverse expansion. They cannot pull distant regions back across the cosmological horizon. They cannot lower entropy globally. Their universe becomes smaller in experience and flatter in possibility. Eventually, interaction inside their own galaxy becomes rare. Stars are gone, matter thins, black holes dominate. Then, even black holes evaporate over incomprehensible timescales. At some stage, the last observer may not have a sky at all. There may be no visible stars, no cosmic background, no detectable external radiation, just internal memory. If intelligence persists that long, perhaps as patterns in ultra-stable structures, perhaps as computational systems operating at extremely low temperatures, it would exist inside a causally sealed domain. No incoming information, no new data, no external influence. That is the deepest layer of isolation. Informational finality. The last observer would not know whether other observers exist beyond their horizon. They could not send signals to find out. They could not receive confirmation. Even if other islands of matter still contain life, they would be unreachable. In that sense, each isolated region becomes its own closed universe. Isolation, then, is not merely physical separation, it is epistemic separation. The most isolated object in the universe might not be a particle or a black hole. It might be a conscious system at the end of time, aware that nothing beyond its domain can ever be known again. And eventually, even that awareness would fade as entropy approaches its limit. The last observer would not witness a dramatic ending. There would be no explosion, no collapse, only the gradual quieting of interaction until thought itself becomes unsustainable. Isolation, in its final form, is not darkness. It is the slow disappearance of possibility. Part 21. Is the universe meant to isolate itself? After following isolation from galaxies to particles, from voids to horizons, from black holes to the last observer, a question begins to emerge that feels almost intentional. Is this separation accidental, or is isolation built into the very structure of the universe? From the first moments after the Big Bang, tiny fluctuations determined where matter would gather and where it would thin. Those fluctuations grew into the cosmic web, dense filaments and enormous voids. Structure formed locally, but separation formed globally. Gravity creates islands, expansion pulls them apart, and then dark energy enters the story. Dark energy is uniform. It does not cluster. It does not weaken in voids. It does not diminish near galaxies. It fills all of space equally, driving accelerated expansion everywhere at once. Its effect is subtle on small scales. It cannot tear apart solar systems or galaxies that are gravitationally bound. But on the largest scales, it dominates completely. It ensures that distant structures do not simply drift apart. They accelerate apart. Why? There is no known purpose. Physics does not assign intent. Dark energy appears as a parameter in our equations, a cosmological constant or something very similar. It describes how space-time expands. It does not explain why. Yet the consequence is clear. Given enough time, the universe fragments. Large-scale structure becomes causally disconnected. Observable horizons shrink relative to total volume. Every gravitationally bound system becomes its own isolated domain. This outcome is not rare. It is mathematically inevitable under current cosmological measurements. And that raises something unsettling. We often imagine the universe as something that expands into openness, an ever-growing arena of potential. But what if expansion is not about connection, but about division? What if the long-term direction of reality is separation? In the early universe, everything was connected in a literal sense. The observable universe today was once compressed into a tiny region of space-time. Particles interacted constantly, energy was shared, there was no void. Then expansion began. Structure formed locally, and the spaces between structures widened. Over time, isolation increases. The cosmic web is not eternal. The night sky filled with galaxies is temporary. The era of shared visibility is fleeting. If you extrapolate forward far enough, every region becomes sealed by its own horizon. Each galaxy becomes its own universe. Each particle becomes its own statistical island. Is this the natural trajectory of entropy? Perhaps. Entropy increases not by destroying structure immediately, but by dispersing it, by spreading energy evenly, by flattening gradients. Isolation is a byproduct of that flattening. Where there are no gradients, there is no flow. Where there is no flow, there is no connection. Dark energy accelerates this process by enlarging space-time itself. It amplifies separation on the largest scales. The universe does not appear designed for eternal connectivity. It appears designed for eventual fragmentation. But here is the deeper reflection. Isolation is not instantaneous. It unfolds slowly over timescales that dwarf comprehension. For billions of years, galaxies interact. For trillions of years, stars shine. For unimaginable spans, black holes dominate. Only in the deepest future does near-total separation approach. We live in the narrow middle, a moment when the universe is structured enough to allow complexity, but not yet so expanded that everything is alone. Perhaps isolation is not the purpose of the universe. Perhaps it is simply the asymptotic consequence of its laws. But from our perspective, it looks like a long, slow drift toward silence. Not violent, not catastrophic, just a widening gap between everything. And that gap, once small and bridgeable, becomes permanent. If isolation is built into the equations of space-time, then the most isolated object in the universe is not a rare anomaly. It is the future default. Part 22. The quietest place that will ever exist. We began with galaxies drifting through vast voids. We followed expansion beyond horizons. We watched stars burn out, black holes evaporate, particles thin into statistical solitude. Now we arrive at the quietest place the universe will ever create. It is not a location you could point to on a map. It is not a region marked by coordinates. It is an epoch, a time when structure has dissolved to its lowest possible complexity, when energy gradients have flattened, when interaction has become nearly impossible. In that far future, space-time continues to expand. Dark energy still stretches the metric. The temperature approaches absolute zero asymptotically. The density of matter approaches zero as well. Not zero in a strict mathematical sense, but so low that events cease to occur. No stars shine, no galaxies collide, no radiation fills the sky. If any particles remain, they drift within horizons defined only by expansion. Their nearest neighbors may lie distances so vast that even gravitational influence is practically meaningless. Quantum fluctuations continue, faint tremors at the vacuum, but they do not build new structure. They do not generate complexity. The universe does not collapse into nothing. It thins into irrelevance. This is the quietest place that will ever exist. A universe where existence continues, but nothing meaningful happens. No new information enters any region. No new connections form. No gradients remain to exploit. Every gravitationally bound island that once shone with trillions of stars has faded. Every black hole has radiated away its mass over timescales so extreme that numbers lose meaning. What remains is a diffuse bath of low-energy particles separated by expanding darkness. If you could observe such a universe, which may not even be possible, you would not see a dramatic end. You would see stillness. Not perfect stillness, because quantum mechanics forbids it, but stillness in every macroscopic sense. No light crossing vast distances, no structure rising from fluctuations, no complexity building upward again. The most isolated object in the universe may not stand out against that background. It may simply be one of the last remaining particles, indistinguishable from countless others scattered across incomprehensible volume. And yet, there is something profound about this ending. Isolation, which began as spatial separation between galaxies, evolved into causal disconnection through horizons, deepened into thermodynamic silence, and culminated in near total absence of interaction. The universe does not rage against itself, it drifts apart. We live in a rare window where connection is visible. The cosmic web spans billions of light years. Light from distant galaxies still reaches us. The sky still contains depth and memory, but that window is temporary. In the deepest future, every region becomes its own closed reality. And beyond each horizon lies a cosmos that exists, but cannot be known. Perhaps the universe is not meant to end in fire or collapse. Perhaps it ends in quiet, not with destruction, but with distance so vast that everything becomes alone. And in that final silence, isolation is no longer a condition of one object. It is the condition of every